reaction we had done. Now we had done esters in the last class. So we're going to start with the formation of amides. So we'll just quickly, and we'll do polymers as well. So formation. No, it's still not working. Just a second. So I'll just cover the remaining reactions. Formation of amides. That is going to happen when you have an amide is Cl bond O and Cl. So an amide is Cl bond O with NH. Again, Scott. That's the group of an amide. That's an amide group. And amides are formed when you have an acyl chloride. So you need an acyl chloride, and acyl chloride is one which has the acyl group, which is CH3, C double bond O, and it's got a Cl. That's what an acyl group is, and it reacts with an ammonia molecule or a primary amine. So it's either going to be ammonia, or in your course, they're talking specifically about primary amines, which is there's going to be an amine group right at the end of the chain. So what will happen is that if I have an amine at the end of the chain, and let's say I've got a propyl amine, there are 3 hydrogens. This one has 2 hydrogens. This one over here will have 2 hydrogens as well. So the H and Cl from the middle would be lost. They're going to form HCl. The reason they're going to be lost is that this carbon, which is strongly positive, it's got a very strong positive charge, will be attracted to the lone pairs on end. So there's going to be this attraction that will happen, and the two things would join up, and they would end up forming an amide group. An HCl molecule is going to be your byproduct. So these things, they would join up. So this will join up, and the middle part will form HCl. So that is gone. The positive carbon and the lone pairs will get attracted to each other, and they would connect together to form an amide link in the middle over here. So that's basically your amide group that's going to be formed. And HCl molecule is going to be my byproduct that is going to be formed. So that's pretty much it. And this happens at room temperature. No specific conditions required. You just mix them together and they would end up forming an amide. The reason the reaction is very fast is that the carbon over here in the acyl group, the carbon is very strong. This carbon over here has a very strong positive charge. So it's very strongly attracted to the lone pairs that you see over here. So that's one important reaction, and I'll just do a couple of reactions of the same time. So that's it. That's how amides are formed. So I'm just going to do a couple of reactions using skeletal formulas as examples. So let's say I have this thing that I have a skeletal formula of a molecule, and that molecule has NH2 on both sides. So over here there is N with 2 H's, and over here on the other side I've got another N with 2 H's. And they say that this molecule is going to react with an acyl chloride. That acyl chloride is this molecule. It's let's say it's ethanoyl chloride. It's CH3CH2, CH3C double bond O, and Cl. And they're asking what is the product of the reaction. So the product of the reaction would be, and let me make a skeletal formula of this as well. It's 2 carbon atoms. Okay, let's make it propanoyl chloride, 3 carbon atoms, and right on one end you've got a double bond O, and you've got a Cl. So that is propanoyl chloride. Now, the product of the reaction would be that this propanyl chloride is going to react with both amines from both sides. So there are going to be two molecules. So let's keep that in the middle. One of the acyl chloride will come and react from this side. And let me rotate this one. That it's going to come in and it's going to react from this side, and the other one would come and attack from the opposite side. So that one, let's make it this way. So all you have to do is you've got to remove the H and Cl that's in between. Make sure the molecules are facing each other in the right way. The H would be lost and the Cl would be lost. So the H and Cl would be lost. So two amides would be formed. This molecule, there would be two of these, because there's a possibility of this thing bonding on both sides. So you got two of these molecules. And then we have the reaction. I'm going to draw the product. The product would look like this, that all you have to do is just remove the byproduct that's going to be formed. And so I'm just going to remove the H and the Cl from the middle. So the H and the Cl are lost. And I'm going to connect the two things together. So the two things will be connected together. So they're forming serial bond O. And in the skeletal formula, they don't show you the carbon atom. So that's about it. So they're basically forming serial bond O and NH. There's NH and serial bond O over here as well. So all you have to do is, if you see an amine, if you see an acyl chloride, all you have to do is connect them together just in this way. They might either show you a displayed formula like this. You'll have an acyl chloride, you'll have an amine, just put them together, that's about it. Remove the H and Cl from the middle and they would end up forming an amide. If it's a skeletal formula like this, you pretty much do the same thing, except make sure that the molecules are rotated or they're facing the right way. The Cl and the H in the middle would all be removed. Okay, is that clear? Sign clear? Munir is... Okay, so that's all about amides. And let me just make sure if the other board, no, that's still not working. Anyways, that's one. Then what are the remaining reactions? You would have to talk about, so we did this, this thing, hydrolysis. We're going to just do that very, very quickly. So you can do the reverse as well, which is you can break this back and hydrolyze it back into, if you heat this molecule, so this is the reverse reaction now. Now, the other reaction that is hydrolysis, you can break the amide back into its components, but you're not going to get the same components. What is going to happen is there are two types of hydrolysis. You either heat it with dilute acid or with dilute alkali. So there's alkaline hydrolysis, there's acidic hydrolysis. So dilute acid plus reflux or alkali. So you can either use NaOH or H2SO4. And you're going to use reflux. And when you do that, the molecule splits up back into its two components. So this thing, if I just copy paste this thing will separate from the other part. See, one part would be this part, and the other part would be this other part, which is this one. So the same amide splits up into its components. But you're not going to get acyl chloride back. Again, what you'll get instead is you're going to get a carboxylic acid, and on the other side you're going to get an amine. So the acyl chloride is never formed. Instead, what happens is you get an amine and a carboxylic acid. So that's an H and OH. So all you have to do is split the thing in the middle, and the two products are going to be formed. And there's another issue with alkaline hydrolysis, which is that if you use an alkali, what will happen is that the alkali would end up reacting with the carboxylic acid. So there's another issue which is specifically for this carboxylic acid.
So these are the products that we get with an alkali?
Not with an alkali. These are the products that you should get, but with an alkali, the issue would be that the carboxylic acid would end up reacting with the alkali. So in alkaline hydrolysis, because carboxylic acid is an acid, so in alkaline hydrolysis, the carboxylic acid group, the COOH group, reacts with the alkali to form salts. So to form salts, and so instead of getting this carboxylic acid, what you're going to get is CH3 double bond O, O-1, and if the alkali is NaOH, then you're going to get a salt of NaOH, which is in this case sodium ethanoate. So that is something that you have to be careful about, because they're going to cut marks for that. So the reaction is simple. You make an amide using acyl chloride. The H and Cl get removed. You break it back into its components by adding dilute acid or alkali. But in that case, you're not going to get an acyl chloride back. You're going to get a carboxylic acid and you're going to get an amine back. And in alkaline hydrolysis, if you use alkali to break it back or hydrolyze it, it's not going to give you your acid. It will react with the acid. So this is the hydrolysis or the reverse reaction. Is that clear?
Yes, sir. Thank you.
Yes, sir.
So for the next one, you've got what's remaining. So hydrolysis with alkali and acids, that's done. We did the acid-base properties previously. We did now this one. Describe the formation of amides, tripeptides. Now this is about polymerization, and condensation polymerization. So we're going to talk about. We're not going to talk about electrophoresis yet. So we're going to do polyamides and polyesters and condensation polymers and predicting the type of polymerization. So that's degradable polymers. So let's start with polymerization. Now polymerization is you've done addition polymerization previously in AS as well. So we're going to first revise that. And we're going to also learn, they've actually removed a lot of things. In this new syllabus, they've actually removed a lot of things. Previously, you would discuss things in a lot more detail, but now hopefully things are a lot simpler. I mean, at least the syllabus is a lot simpler when it comes to polymerization. Now, polymers are number one, the previous one. That's your addition polymers. Now it's mostly like your O-level stuff. So addition polymers. Now, when you have addition polymers are made from alkenes. So the monomer is an alkene. It's an unsaturated, it's an alkene or it's an unsaturated molecule. It's got to have double bonds. So you need at least carbon double bond, carbon somewhere in the middle. And so we'll do just one example. At least a couple of examples just to show you what's going to happen. So they talked about predicting the type of polymerization. So if the monomer is an alkene, it's going to be an addition polymer. That's pretty much a given. And this is kind of simpler. You don't even have to remember the conditions. Usually it's high pressures, high temperatures. So if you have an if you have an ethene molecule, and let's say you have lots of ethene molecules, what will eventually happen is, let's say there are two more. So what will eventually happen is that these ethene molecules, they would all just join up. The double bonds in the middle would go away, and the double bonds would turn into single bonds. So that's the reaction. So under high pressures, high temperatures, you compress them together, so all their double bonds would turn into single bonds. So those are the double bonds vanishing. Now the carbons are short of one bond, so what they'll do is they'll start linking up, and so the carbons would start linking up, forming a chain of many monomers joined up together, so forming a macromolecule. So that's what this polymerization is all about, and that results in the formation of a very saturated carbon chain. So that is what addition polymerization is. Is that clear? You've done that in O-levels as well. You're doing this again now. Is that clear?
Yes, sir.
And also remember that. Also remember one more thing about this is that. So I'll do another example, like a slightly more complicated molecule. Now this is if your monomer is ethene. So if your monomer is ethene, your polymer is going to be polyethene. So the name of the polymer would be polyethene. Just means that it's a multiple of ethene. So that's a polyethene polymer. Now let's do a slightly more complicated one. Ethene is kind of easy. Slightly more complicated. Let's take a bigger molecule, and let's say it's an unsaturated molecule, and it's got double bonds. So you got CH3, CH2, and there's a double bond over here, and there's a carbon atom. There's a CH3. Let's say there's an H, and this one has. Let's say this one has a carbon atom, and it's got another carbon chain, which is CH2, CH3. Now, what I'm going to try and do is I'm going to try and make a polymer out of this monomer. So that's my monomer. And let's try and make a polymer out of it. Now, the rules for making polymers is out of alkenes is that it's the double bonds that are reacting with each other. It's the double bond of one carbon atom that's basically reacting with the double bond of the neighboring carbon atom. The rest of the molecule is not doing anything. It's just the double bonds that are reacting together and forming bonds with each other. Now, if I take this molecule, the first thing is your focus is on the double bond. It should be on the double bond. Make sure nothing should be drawn on the left side or the right side of this double bond. So the first step is redraw the monomer. What you're going to do is you're going to redraw the monomer, and this time be careful. Don't keep any group on the left or right side of the double bond. So don't keep any group on left side or the right side of this double bond. So I'm going to try and do that now. I'm going to try and redraw this thing. So let's say this is my monomer. What I'm going to do is nothing should be on the right or the left side of this thing. So the CH3 over here, which is on the right side, this one. So this CH3 over here should not be on the right side. And this CH3 on the left side, it should not be on the left side. I'm not going to break the bond. What I'm just going to do is I'm just going to twist the molecule a bit. I'm going to bring the CH3 or bend it upwards. Remember, no bond breaking. It's just that you have to sort of redraw this in a way that it becomes easier to connect two monomers together. So that is what we are after. So we're just going to redraw this molecule so that it's easier for us to make the polymer. So if I redraw this, so I've got a double bond in the middle. The CH3, which was supposed to be on the right side, I'm going to bend it upwards. So that's pointing in the upward direction. And the CH3, which was on the left side, that's also now pointing in the upward direction. What's pointing over here? There's an H at the bottom. And there's a CH2, CH3, let's call that, let's make it CH2, CH3. So this is all that I have done. I've just redrawn the molecule. Is that clear?
No, sir. Can you kindly repeat it?
We're not doing anything. All we have to do is, the reason we're doing this is, okay, the double bonds must be next to each other because it's the double bonds that are reacting together. So the first step is that you have to, if you're given a monomer and it's an alkene, the first step is you've got to redraw this. That's the rule, that the double bond, there should be nothing on the right side or the left side. The reason we want that is because it's the double bonds that are going to react together. So it's one monomer reacting with the neighboring double bond. So it's easier if the double bonds are facing right next to each other. So this carbon over here in the double bond should react with the carbon from the neighboring double bond, right? So if there's a CH3 that's on the right side, so that CH3 would interfere. Let's imagine that this CH3 over here, this one, is facing this direction. So there's going to be a problem here now because the CH3 is coming in the way, right? If I keep this CH3 on this side, it's coming in the way. Do you get the idea? Is that clear?
Yes, sir.
So what I do instead is, okay, I take the CH3 and I'm not changing the molecule. What I'm just doing is, I'm just drawing it in a different direction. I'm just changing the direction. I'm just making it go up. That's about it. So these two CH3s, this molecule over here is exactly the same as the molecule that's drawn above. The only difference is I've just bent the CH3s upwards. The CH3s are now over here and this one is over here. Is that clear?
Yes, sir.
And the whole purpose of doing that was so that it becomes easier to connect them together because the double bonds would react with each other. So the next step would be easy. That if I have, let's say, 4 monomers join up, what's going to happen is that the 4 monomers would connect with each other. Their double bonds would connect with each other. The rest of the molecule remains exactly the same. So all that happens is that these double bonds, they turn into single bonds, and your molecules, they start connecting with each other. And that's going to be your polymer. Just wait 1 second, let the board load. So we're just going to get rid of it's still not happening. Just a second. Sorry, I did it on the top one. So it's basically in the reverse direction. This one. So what has happened is that the double bonds have gone and the molecules, they have joined up. Is that clear?
Yes, sir.
So remember, this is slightly tricky because ethene was easy, but the rest of the ones would be slightly more complicated. So if I draw another one, and the way to write this is, they would either ask you to draw 2 or 3 repeat units. That's a repeat unit. Or what they can ask you is, or the other representation is that you draw just one of them. just draw one repeat unit. And once you have that repeat unit, all you have to do is you would have to just put brackets around it and write N at the bottom. So either it's curly brackets or square brackets, doesn't matter. So that's another way of representing this molecule. So make sure you read the question properly. They might either ask you to draw 2 or 3 repeat units, or they might just ask you to, or if it's an open-ended question, you can just draw this. That's the repeat unit. So here's another molecule. I'll just quickly do that one. If I have another polymer, addition polymer, I want to make an addition polymer. So I've got CH3, CH2, and there's a C double bond C, and an H and another H. Now the quick way of writing this molecule is just wait, the board is stuck. You just hold on a second, let me reload this. So I wanted to use that board because we are making notes with that. But we can sort of it's still not working. As anyway, so I'll just quickly do another example here that I have a molecule and I've got a double bond over here. So if I want to write this as a polymer, if it's making a polymer, the first thing is double bond. Nothing should be on the right side or the left side of this molecule. So there should be no H, there should be no CH, this thing on the right or left side. So what I'm going to do is change their direction, like bring the H downwards, bring the CH2, CH3, CH2 downwards as well. So we're going to keep the double bond in the middle. Nothing should be on the right side. So this H over here, I'm going to pull it or bring it downwards. And this entire group over here, CH2, CH3, I'm going to do that, the same thing with this one. Instead of drawing it on the left side, I'm going to draw it downwards in the downward direction. And that's pretty much going to be my monomer. And the next step would be just hold on. So I'll have to manually write this. So the next step would be that these would join up, and that's about it. And I'll have CH2 and CH3, and I'll have H over here. The double bond would go away, and they would link up. Is that clear?
Yes, sir.
So so the board is back. Just hold on a second. So we're going to talk about this a bit. Just some extra information. This is something that we've already done in O-levels as well. So just some extra information regarding this, and that extra information is about the properties of these addition polymers. The first property is that these are non-polar chains. A carbon chain, it basically ends up forming a carbon chain as shown above. So these polymers, especially addition polymerization, they're non-biodegradable. So coming back to this, sorry. No, still not back. So about these carbon chains, one of the major properties is that they are non-biodegradable, or they biodegrade with a lot of difficulty. The reason behind that is that when you have a carbon chain is a non-polar chain. Carbon chains are non-polar, and usually what happens is carbon-carbon bonds are very stable. Because of that, because they are non-polar chains, so they happen to be very stable bonds, and which makes them very unreactive. So plastics are usually made out of these types of, like your plastic bags, they're basically polyethylene molecules. It's basically ethene molecules joined up the way that we did earlier. So when you have these ethene molecules joined up, they are pretty much going to be unreactive, and they're going to be hydrophobic as well. They're only going to have van der Waals forces because of their non-polarity. So they're not going to attract water as well, because water forms hydrogen bonds. So all these polymers, the ones that we have discussed so far, they are kind of non-biodegradable, kind of unreactive, not very attracted to water as well, so not very soluble as well. The other properties about this is that that the carbon chain can have many side chains. Like if you look at the molecules that we did earlier on this particular, no, it's still gone. So if you look at the molecules that we did earlier, polymers can have lots of side chains. Now this is something that's very important. Can have many side chains and branches and cross links as well. And these would change properties. So the one that we showed over here, this one, you can think of this as a thread, like your normal thread. That's a polymer basically. So think of these as strands, tiny strands. Your hair is a polymer, your skin is a polymer. Think of this as a tiny strand, and there's a strand, a very nanoscale level strand, which has these carbon chains coming out of it. So that's your polymer. So when you think of it like that, so polymers are like these tiny microscopic strands, and there would be tiny strands that would be coming out of it. So that's one way to look at a polymer. So you will have all sorts of polymers. Some would have very big side chains. Some may not. Like ethene over here does not have a side chain. An ethene molecule has absolutely no side chain because all of them are hydrogen. So what difference does the side chain make? So think of a polymer that doesn't have a side chain. That polymer strands could be entangled. That's what plastic is. Like if you look at plastic under a microscope, I mean, you'll probably not be able to observe this, but at the nanoscale, your clothes are kind of are basically made up of polymers. I mean, if you look at your sweater, that's lots of tiny strands, all entangled with each other. So plastics, I mean, your laptop plastic, your keyboard plastic, your etc. They're all these tiny strands all entangled with each other. And what happens is that if there aren't a lot of side chains, they can be closely or tightly packed. So if it doesn't have side chains, they can be tightly packed. They can be tightly packed, and what else? So which means they would have high density. So they're going to have high density. And it would be easier to slide those one of the thread out of it. Like if you look at the plastic polythene bag in which you carry foodstuff and you carry your shopping bags, you can easily stretch it. When you stretch it, the strands become loose. You can pull out the strands when you're stretching it. That's what's happening. But what if a polymer chain has lots of side chains? Like the polymer has a lot of strands. Then what will happen is there would be a lot more entanglement. It would be harder to sort of pull them apart because those branches that are coming out of it, they would be entangled with each other very, 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 very strongly. So in that case, if the polymer has branches, then there's going to be more entanglement. And it's going to be a stiffer or a stronger polymer. So you would have, I mean, you can think of the shopping bag that's like soft. The strands can easily be pulled out, like you can stretch it in different directions. But if it's got many side chains, then the entanglement is like a lot stronger, and you can't really sort of twist it around. They would be entangled with each other very, very strongly, so you can't really stretch it. So like your keyboard, plastic keyboard that you have, you can't do that with that. You can't sort of twist it around. You can't. So it's going to be a lot harder. Is that clear? Is this the same? Munia, is
Yes,
this
sir.
clear?
Yes, sir. Thank you.
Plus, it's going to be low density as well, because the chains will not be very close to each other. So think of styrofoam. Like styrofoam is very low density, but it's very stiff. I mean, it doesn't. You can't really. If you try to bend it, it breaks. So styrofoam is very low density because a styrofoam polymer would probably have a lot of side chains, which would keep the chains very far away from each other. So this is one thing that you should have an idea about, that that you're going to have polymers, and polymers can have many side chains to go with them, and there would be many branches and crosslinks, and the properties of the molecule would change. There's another concept which is cross-linking, that if you have two polymer chains, then there could be certain groups that could be attached on the polymer chains. Like there might be an OH group on one chain, and there might be a carboxylic acid group. There might be a carboxylic acid group on the other chain. So what can happen is that the side chain would react with each other, and when they react with each other, they would, I mean, if a carboxylic acid reacts with an alcohol, it ends up forming an ester link. So that's known as a cross-link. So all types of bonding can happen or take place while the side chains interact. So the chains that we did over here, I mean, the board is still lost. So the chains that we did over here, if you have side chains which are reactive, then they would, I mean, you can have an OH group on one chain and you can have an OH group on the other chain, and they can form hydrogen bonds with each other. Maybe there's a carboxylic acid group on one chain and there's an ammonia group on the other chain, which is basic. So they might end up forming an acid-base reaction, and NH4 plus one might be produced. So all sorts of interactions are possible between side chains. So that's another thing. So there is no side chains. Molecule is the chains would have lesser interaction with each other. If the polymer has more side chains, it's going to be a lot stiffer. It's going to be a lot harder. The side chains would start interacting with each other. They would start entangling with each other. And the last part is that maybe the side chains, they start reacting with each other. So the polymer thread that you have, the tiny strand, microscopic strand that you have, they might end up bonding with each other in some way. And that's known as a crosslink. And crosslinks can be of any type, like any bond imaginable, any attractive force imaginable, that could be a crosslink. So is this clear?
Yes, sir. So one question. in between which molecules does cross-link develop? Like, are there any specific?
Hey, it could be any molecule. Like if I any molecule. Let's say I was making a polymer out of this alkene. Okay, and I'm making a polymer out of another alkene which has a side chain of a carboxylic acid. Like there's a carboxylic acid present, right? So when many of these would join up, there's always going to be an OH group that would be coming out of it, right? Because the original molecule had an OH that was coming out of the carbon chain. Is that idea clear?
Yes, sir.
And there's this other molecule, and this molecule will have, like when I polymerize this, think of the carboxylic acid group that would be coming out of it. So when I talk about crosslink, it's I'm using the word in the most general way possible, that you can think of anything like the branches that are coming out that we drew earlier, TK, that we did a bunch of like these branches over here. If you hopefully the board works, like this branch over here, it could be any branch. TK, it could be any sort of molecule, and it could interact with the other neighboring carbon atoms branch, and they could sort of bond in many different ways. Is the idea clear? Alicia, clear?
Yes, sir.
So plus they're not going to be very specific. So anyways, let's continue tomorrow. The board is still hanging up. So let's continue tomorrow. And we'll try and finish condensation polymerization as well. Okay, just remember this last part that we did over here. Okay, what effect would side chains and branches and crosslinks have? And also remember how to make a polymer. Like if you want to make an addition polymer, make sure that nothing is drawn on the left or right side of the double bond. And that's pretty much it. Non-biodegradable, remember alkenes, polyalkenes, or polymers made out of addition polymerization are usually non-biodegradable. So let's continue with this tomorrow then.
चलो सर
Okay. Love it.
Thank you, sir.